Cool. And we are back for another episode of High Stakes Mathematics. I hope you're ready for a bit more exciting action. So we started out, we did a lot of in the arithmetic section, and now we're moving on to the number theory section. We did some divisibility test last time, and we're going to go on to primality test this time. So that means, is a number prime or not? So 1 and 20 are the only positive numbers that divide 20. So it's basically asking, is number 20 prime, right? Well, I think quite obviously the answer is no, because you can have 4 times 5 is 20, or 10 times 2. And I think an appropriate theorem for proving that is this NPRMI. And it basically says if A and B are natural numbers, A and B are larger than 1, so they can't be 1, then you have A times B equals N, then N is not prime. Okay? So I think it shouldn't be too difficult to... what we're looking to prove here. We're looking to prove that not true 20 is prime. And like this. Okay. So we'll have 1000. We'll have one of these. Right. And then we'll have 20. And what do you think we should pick? 10 times 2 or 4 times 5? I think maybe 4 times 5 is easier, because 10 is one of those decimal numbers and 4 and 5 are just really simple basic numbers. And there you go, boom, 20 is not prime. So that was really very straightforward. So the answer is false. I don't know what is up with Wolfram Alpha. Like, why does it do this? Why does it say I can't accept, I'm just clicking a button, mate. I'm just clicking a button. All right, well, we know we got the answer right. So let's try an advanced problem, right? Is 159 prime? Good question. All right, let's just go through. Could it be 2? No, it's definitely not even. Could it divide by 3? I think 120 divides by 3. So 150 divides by 3. So 159 divides by 3. Oh, that's quite interesting. So it's 53 times 3. So it's not prime. So I don't think we want... I'd like to do one which is prime to show that it's 91. Is 91 prime? Does it divide by 3? No. Does it divide by 5? No. Does it divide by 7? Yes, it does divide by 7, because it's 23 times 7. So that is false. Let's see if we can find one where I'll just do it in Google. Is that easier? Is 219 prime? No. Can we please have a prime number? This is not that big of an ask at Google. 113. 113 is a prime number. Okay, so we have to prove that 113 is prime. So let's get rid of the proof. Let's get this QED going. 113 dot prime. And we haven't got any steps so far. Okay. So how do you in metamath prove that something is prime? So I found a couple of really nice theorems which are going to be very useful. So in this prime section, if your number is less than 25, there is this prime lemma 1, which says that if n is a natural number and it's greater than 1, and 2 does not divide it and 3 does not divide it, and it's less than 25, then n is prime, right? Which is quite helpful, because any number, like basically any prime number, if it has 2 factors, one has to be bigger than the square root and one has to be smaller than the square root, right? Because, or they can both be equal to the square root, but like you can't have 2 factors of a number that are both bigger than the square root, because otherwise when you multiply them together it would be bigger than the number itself, right? So we can't have that. And so this is quite a simple theorem, and then they extended it to do numbers up to 841. So prime lem 2, we can say anything up to 841 is not prime if it doesn't divide by 2, 3, 5, 7, 11, 13, 17, 19, 23. Okay, so this is going to be a bit exhausting, but it's all quite straightforward stuff, right? And I was just going to check. They might have proved it here. It's like they might have done it as a example number, but they haven't. And then they also have some of these very large primes which they proved kind of by themselves. But I think if the number we'd picked was higher than 841, or the number that aliens had picked was higher than 841, we were going to have a bit of a struggle proving it. But luckily 113 is in that range, so it's okay. And it's a bit of a overkill, because 11 squared is 121, so that's already too high, and then proving that it's divisible by not divisible by 13, 17, 19, or 23 is too much. But that's life, I guess. Sometimes you gotta work for a living. Okay, so that's all we need to prove, and we wanted it to be 113, like this. I think that will, yeah, it moves the QED up one step because it can do that. Okay, so it's already got on quite well with it. It's, why is it asking if 113 is less than 9? I mean, we're going to have trouble proving that. D21, where is D21 used? Why has it even put that in? So I don't think that's doing anything. Oh no, there it is, the line below. 113 is less than 841. Okay, so we do need this, but we don't need the step above. Because, yeah, I think that was wrong. And yeah, we just have to read these things. And one thing that's really helpful that I managed to find is this theorem, NDVD-SI. And basically what it's saying is if you have a natural number and a counting number and a remainder, then if you can prove that A times Q plus R equals B, and R is less than A, then A doesn't divide B. So basically what you're saying is if I have like 23 times 7 plus 2, well 2 is less than 7, and therefore 7 doesn't divide B because it's just above a multiple of 7. And I think this was largely what we used last time, but I think this is rather easier because you just have to construct this, which I think is really not too difficult. And then these are very simple, and that's very simple, and then you get this result quite easily. So we're going to just have to do that a bunch of times, okay? So we've got not 2, not 3, not 7, 11, 13, da-da-da. And let's just see if there's any more of these we need to finish off. So we need to prove that 113 is less than 841. And I don't know exactly how to do that. I wonder if I can have like, if I do like 13 is less than 41, I don't know if it will like allow that. Yeah, now it's saying 13 is less than 9. So what's this? 1 is n and 0, 13 is n and 0, 13 is less than 9, therefore 13 is less than 41. 4 is a natural number. What is going on? Wait, what was it called? Dec LTDI. Dec LTDI. Okay. So if C is less than 10, so this is a slightly different one, but if C is less than 10, then C is less than AB. Well, that kind of makes sense. Can we get some things? So C is less than 9. So this is a way of saying it's less than or equal to things. But we need something for about if 2... C is less than T. C is less than T times A plus B. This is actually more difficult than I thought. What about this? Take a bunch of natural counting numbers. C is less than 9, A times B is less than A times C plus D, BD. So what am I trying to prove? I'm trying to prove... Because I was thinking if I did 13 less than 41, but if I did 11 is less than 84, right, then... I wonder if I can do 1 is less than 8, and then 11 is less than 84, and then 113. I wonder if that would work, right? So let's do 1 is less than 8. Okay, you'll be happy with that, right? And then let's have 11 is less than 84. right? Which I think does follow from that. It's keen to use this theorem, which is not the right one. Yeah. If B is less than C, AB is less than AC. If A is less than B, A... Okay, I think this will work. I think that will work. Declare. Let's try that. Okay, so we don't want this. We don't want this. Okay. So we have, and what if I wanted 11 is less than 84? 11 is less than 84. We just need 1 is less than 9, but I think that's not going to be too difficult to do. Right, so that should fold that in. Interestingly, that didn't use 100, okay. And then are you happy with 113 is less than this? No, because it's doing the same thing again. Metamath. Misbehaving. Okay. So what's DECLTH? C3 is less than 9. Yeah, so if you had 11 is less than 9, then we could have 113. But what if I put in for C1, I put in comma 1, 1, and what if I put in C3 is only 3? Is that allowed? And then this is 11. Right, and then this, I don't care which way around it does, 841. Yeah? So I have 1 less than or equal to 9 and, making some progress here. Let's see, 105. 1 is less than 9. Yeah? Oh, come on. Surely if 1 is less than 9, 1 is less than or equal to 9. Didn't we do this already? I swear I did this. Less than or equal to real or something? Less implies less than or equal to... No. What was it called? I swear we came across this before, right? Where we had something is less than or equal to something. Something is less than something implies something is less than or equal to something. But I can't remember what the theorem was called. Like, it's this implies this. And I think maybe it needs like, yeah, LTLEI, less than imply, less than, okay, yeah. Okay, so it's this. Oops. But we want to apply it here. So we want to have 3 is less than 9. This is going to be a monster proof. And then we want to have, if it's taken this long just to get out of the weeds, 3 and 9. Boosh. Okay. Now we're starting to make some progress. Okay, so done all that. Blue, 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 blue. Very satisfying. I like it when it's blue. Okay, so then D2, that's satisfied by 300. Should probably delete it. Right. What else have you got? Okay, so we've got to here. Right. Cool. And interestingly, it's done not 5 divides 113, and I don't know why it's done that. Dec 5 DVDS. So it says, oh, interesting. Yeah, okay, so if it knows that if the last digit is not a 5 or a 0, or if it's less than 5, then it doesn't divide. That's clever. Okay, well done, whoever put that in. to get to prime lem3. Okay, so let's start from the bottom with some of this. 10,000. Boop. Okay, so this is what I want to prove. And the question is, how many times is 23? What's the closest divisor, right? So 23 times 5, I think, is 115, so that's too much. So 23 times, no, it's not. 23 times 5, yeah, it's 115. So 23 times 4 is 80, 92. 92, and then I need another 21. Yeah, you like that? Nice. Okay. I think that's all worked out. This is the power of MJ2, and it really gets rolling. It's really done a huge amount for me. Thank you, MJ2. Okay. One down. Bunch more to go. No, what do I call this one? 10,000. Call this. What do I call it? 100,000. 10,000. Okay, I'll call this one 9,000. No, oops. NDVDSI. NDVDSI. This is what I want to prove. Bung that in. 19. 19 times 4. Well, 19 times 5 is just a little bit less than 100. So that's like 95, right? Is that right? 19 times 5. 95 plus... Oh, okay, let's just do 113 divided by 19. We get 5.9. Okay, so it's 5. I want 19 times 5. And I want the difference is 95 is 18, right? 1, 8. Boosh. Okay. Feeling a bit suave all of a sudden. I think that's done everything. Okay, so 8,000. DVD SI. I want to prove this. Getting a bit of production line going here. 113 divided by 17 is 6. So 6 times 17 is 60 plus 42 is 102. So that will be 11, I think. Yeah. Okay. 8,000, 7,000. And DVD SI. 7,000, 13. 113 divided by 13 is 8. 8, and that's 80 plus 24 is 104. So that would be 9 left over. Which all seems a bit easier because the remainders are smaller. But metamath, MMJ2, doing it a monstrously wonderful job all by itself. And DVD SI. This is what I want to prove, please. So I think this is going to go to 110 with remainder 2. No, remainder 3. Yeah. And then this will be 5,000 and DVD SI. Prove this, please. Just do it here. 16. 7 times 16. So what's 7 times 16? It's 70 plus 42, which is 112. Remainder 1, huh? Very close. Very close. That is as close as you can get. And we just have 2 more left because it did 5 automatically. So that is number 4,000. And DVDSI. Prove this, please. I think it's going to go into 112. Is that right? It goes 90, and then it goes into 21, so it goes into 111. So that would be 37 times, I think. 37 times with remainder 2. Yeah, loving it. And 3000 and DVDSI. Proof this, please. Obviously that goes into 112, remainder 1. And it goes 56 times. 56 times into that, remainder 1. Metamath proof generated. Look at that. That is a real beast too, huh? Look how many steps this proof has. I mean, a lot of that is to do with the fact that MMJ2's filled a lot of it in for us, because it's done a lot of these little steps, proving things in natural numbers, improving these multiplications together. That's a bit annoying. I'm a bit annoyed that that's not easier, that you can't do this less than or equal to thing easier. I'm pretty proud of this proof though. Like, look at these D's, they go up to like 222, so our proof's got to have like 230 lines, 240 lines or something. Just a pretty big proof. Yeah, and we are definitely, absolutely sure that 113 is a prime number. Okay, with all of this proof, I'm going to save this because I like this. 113 prime, save. Answer, we're going to risk Pittsburgh. Okay, you're safe for now. Safe for now until next week. Let's see what's next. Coming up on the roster is prime factorization. Oof. I think that's going to be really hard. Like, an interesting question about that is like, what does it mean? I'm going to have to think about that in between the episodes. Like, what does it mean to prove that something is the prime factorization of something else? I guess it means that you need to prove that each of them is prime, and that when they multiply together, you get the result. But I'll have a look and I'll think about it and I'll get back to you. I'll leave you on tenterhooks for the thrilling next installment of High Stakes Mathematics. All right, thanks for watching. Really appreciate it. And yeah, I'll see you in the next one.